which is, did I calculate standard error? I didn't calculate. Whoop. I got ahead of myself. Oh yeah, I got ahead of myself. Let's calculate our standard error. Our standard error finally is equal to is equal to. I did the standard error. Well, I kind of got lost here a little bit. This is 1 over n. This is this, and this is. Yep, this is my standard error. I got it, I think. Okay, so now my z-score is equal to, hopefully you'll be able to follow it because I'm trying to do 9 things at once over here, is equal to this, my differences divided by my standard error, which it finally comes down to, and I get a z-score of 2.87. Okay, what was our critical value of z? Our critical value of z was equal to 1.64. If it were two-sided, it would have been 1.96. So it seems like in this case, we wind up with the same result, which is, I don't think you're going to have that's why, I'm thinking that it's most likely that, and you can use the same reasoning as I do. I mean, if you got one problem, it's going to take you an hour to do, then Kara, thank you. I realized it after a while. It was that I already calculated standard error. I'm going to put those into that. I just started that reference section that you guys were talking about. You may notice that there's a PDF file that has all of the tables that you'll most likely be using for this, and probably even for the final, is under new reference tab that's on Blackboard. I'm going to make up something and put these formulas in there, the various formulas. I'll try and summarize as many as I can for you. So in either case, we would reject the null hypothesis here that the drug is equal to or less than the placebo, and accept the alternative hypothesis that indeed the rate of anxiety if you took the drug is lower than the rate that if you took the placebo. Okay, so the only other thing I wanted to mention, because we really ran out of time a while ago, was let's see. Oh yeah, we got the same kind of problem when we deal with numerical variables. Now, in those cases, we're going to have a situation where we're dealing with a numerical variable. We're going to have a situation where you might have a sample of 60, sample size is 64, right? Take 64 people, and their average BMI is 26, and you might have another sample of 64 and independent sample BMI, and their average BMI is equal to 26.9. Okay, and you want to be able to say, whether, let's say this is group A, this is group A, and this is group B, right? Your null hypothesis might be that BMI, the mean X bar for A equals, or rather, excuse me, really, since it's a hypothesis, mu for group A is equal to mu for group B, and so on and so forth. And you know that the way you would do this is that you'd calculate your z-score just like we did before, and you use, like the 26.9 minus 26, difference between the two means over the standard error. Well, now here's where things get a bit complicated. This is a numerical variance, not a proportion. So we have a whole new set of formulas for calculating the standard error, right? And there's two ways that we could look at this. We could look at this that from the perspective that the standard error, that since the standard error involves, in the simplest form, when we did a single sample example using numerical variable, it's just equal to the standard deviation divided by the square root of n, of the sample size, right? Pretty simple. Problem here is that what's the standard deviation? Okay, well, and you have two samples as well. Sometimes you have same size samples, sometimes you have different size samples. Well, the standard deviation, you could look at it a couple of ways. One way is that the standard deviation for group A, is different than the standard deviation for group B, and that can happen. You could find that whatever is increasing the BMI for this group is also affecting the variability. So it's not the same variability. So you have to use a formula to calculate the standard error that produces a standard error that you could use in your formula that takes into account that, like, the standard deviation in the two samples are different, right? Because kind of you got, and now let's say that, and more often than not, the standard deviation, and usually even within your null hypothesis that there's no difference. Well, one of the no differences is that standard deviation of the two of these is the same. Well, you can get a bit of an advantage by combining the two of these to calculate the standard deviation, right? So there's formulas that you use for calculating the standard deviation. Let me see if I got a couple of them here. Two dampened proportions. Okay, here's our t-test for standard deviation. Okay, T or Z, depending on the size of the sample. Again, okay, with samples, okay, X1 bar minus X2 bar. That's what we see over here, right? Now, this other part over here, mu1 minus mu2, you're making in your null hypothesis the assumption that this is really comparing the differences between the two groups. You might notice SPSS, when it puts some data out, it actually gives you it doesn't really give you these numbers. It really gives you kind of a difference between these numbers. Okay, so now this mu1 minus mu2, by definition, your null hypothesis says that these two are equal. So we just drop that part out. You can ignore that when you see it in the formula. You're really just looking at a t-score of x1 minus x2 over the square root of the over your standard error. Well, standard error is going to be standard deviation over the sample size, over the square root of the sample size, right? Well, problem is that this group's got its standard deviation, this group's got its standard deviation. And if you're getting it from the samples, they're not exactly the same number. Okay, so what you can do is that you can say to yourself, well, gee, I'm going to find a pooled standard deviation. That involves another formula. Just like we had a formula for proportion for kind of a pooled standard deviation, there's a formula for doing that for these samples as well. Once you calculate that pooled standard deviation, you can substitute it into this formula for the standard error. Standard deviation pooled squared over n minus 1, standard deviation pooled squared over n2, and take square root of that and divide this into this, get your z-score, and do exactly what you did before. Compare it to the critical value. Okay, let me see if I can't find that formula so you can get a look at that. Now, is it likely you're going to be doing this kind of stuff on the exam? I don't think very likely, because this is so time consuming, right? Especially if you don't have SPSS and Excel in front of you. Formula, independent samples, t-test, pool standard. Here's the formula for the pooled standard deviation. Okay, it's the sum of squares for the first group plus the sum of squares for the second group over the degrees of freedom for the first group over the degrees of freedom for the second group. Well, what's the sum of squares? The sum of squares is the standard deviation squared times the degrees of freedom. A little confusing, right? Okay, think of it this way. The way that we got standard deviation, right, was we took the sum of squares divided by, we took the sum of squares divided by the degrees of freedom to get the variance, and then took the square root, right? So you're doing the opposite here. You're taking the standard deviation, squaring it, and multiplying by the degrees of freedom to get this number. In other words, 1 minus 10. Just so for this sample, it would have been, did we give us, I didn't give a standard deviation here. Let's say standard deviation here was 3. Standard deviation was 3. Then this for that group would be 3 squared, which is 9, times 63, which is the degrees of freedom. So it would be 3 squared, 9 times 63 would give you this number. And this number down here would be 63. So for the other group, if it's the same size sample, this would be 63 down here. And if this had um, a similar a standard deviation, we'd also do that, calculate that for a pooled standard deviation, and then this would be used in this formula here. I'll try and put these all together, but I don't think, except for except for uh, uh, kind of interpreting stuff, I don't think you'll see too much of these of examples that will require you to do lengthy calculations by hand. I think it's more likely you'll get some interpretive stuff where it can be kind of work for you. As you'll be given examples of outcomes and so on and so forth. Maybe even tables from SPSS that have been worked out, or results of analyses, ask you to interpret them and so on and so forth. And maybe some very simple examples that would ask you to do the calculations. And most of the very simple examples usually involve, as you can see, single sample